Okay, thank you for the introduction. So, as you already said, my name is Marko Petrovich. I come from the University of Delaware, and today I'm going to talk about, I'm going to repeat this long title, first principle theory of proximity spin-orbit torque in two-dimensional magnets. And in particular, I'm going to talk about the current-driven antiferromagnet-to-ferromagnet phase transition in bilayer CRI3. So this is a work which is done at our group under supervision of Professor Petr Plehač and Professor Branislav Nikolic. So first, let me give you an overview of the talk. So I'll briefly touch on the area of 2D magnetic materials, and then I'm going to talk about a specific magnetic material called CRI3, and I'm going to talk about an experiment in which they basically perform the antiferromagnet-to-ferromagnet phase transition in this bilayer CRI3. Then I'm going to present you our proposal to do this transition in a slightly different way using a proximity spin-orbit torque. And the rest of the talk is basically on how we model the magnetization dynamics in these bilayers, and in the end I will show you two videos of how the magnetization behaves. Okay, so we start with 2D magnetic materials. So as you all probably know, with the discovery of graphene, you had an opening of this field of 2D materials. And then people start stacking these 2D materials in different ways. I mean, they use different materials and they stack them in different orders. And depending on the type of material and on the stacking order, you can have different properties. And very recently, in the last few years, there is an increased research in the area of 2D magnetic materials. Now, in 2 dimensions, if your material can be modeled as with a Heisenberg model, so if it's like isotropic, then there is no 2D magnetic order at the finite temperature because the spin waves will simply destroy any order. So in order to have magnetic ordering in 2D, you need to basically confine the motion of your magnetization. And this is usually if you have some anisotropy in the system. So the basic property of all these 2D magnetic materials is that they have a perpendicular magnetic anisotropy, or any anisotropy. And what's also interesting, if you have, like, they don't have to be just one layer, they can have like few layers. And they can have different ratios of interlayer and intralayer exchange coupling between the magnetic moments. So here I present like four different configurations depending on the ratio of these two, like intralayer and interlayer exchange coupling. So you can have a material which is like a ferromagnet inside of a layer, which could then be coupled ferromagnetically or antiferromagnetically with the other layers, or you can have a material which is antiferromagnet in a layer, and then you can also have ferromagnetic and antiferromagnetic coupling between different layers. And here also it's a list of these recently discovered materials and how they fit into this picture. Now we're going to look at one specific material, which is this CRI3, and this material looks something like this. So it's the lattice consists of these chromium atoms, which are these white spheres, surrounded with the iodine atoms, which are these violet spheres. And in a single layer, as I already said, the material has a strong perpendicular magnetic anisotropy, so the magnetic moments are basically they either point up or down. And what's also interesting is if you stack this material, so this is for a single layer, but if you stack it in 2 or 3 layers, although each single layer is ferromagnet, you can have this interlayer. You can have different coupling between the layers. So for 1 layer and for 3 layers, you have a ferromagnetic coupling, but for the bilayer system, you have an antiferromagnetic coupling. So basically, these experiments are this experiment is basically measuring this magneto-optical Kerr effect. So basically, they shine a laser light onto this system, and then they measure what is the change of the polarization angle of that light, and then that basically tells you what is the value of magnetization in the layer. So basically, in a single layer, you have this 2 different angles, and then you have this loop here, which basically tells you that this is basically a signature of a ferromagnetic phase, and this is also for the same for one layer for layer system. In a bilayer, for zero field and for small fields, there is no this Kerr angle. That's because basically you have a positive angle for example, for a first layer, a negative angle for the second layer. So basically they cancel out, and this is basically a proof that you have an antiferromagnetic phase. And then as you increase the field, for higher and for very high and for not very high, but for higher and lower fields, these magnetic moments in the upper and lower layer can flip, and then you basically have a ferromagnetic phase, either both moments pointing down or up. Now there is a variation of this experiment where they place two gates on top and on below the bilayer CRI3, and this is basically more or less the same as in the previous one, but now you have an extra controlling mechanisms, right? So this graph is the same as previously, and this is for zero bias. But now you can basically electrostatically change the bias voltage on these two layers. And when you swipe the gate potential, you get something like this. So on the edges you have this blue and red region, which are basically a ferromagnetic phase of both magnetization pointing either down or up, and in the middle you have this white area, which is basically an antiferromagnetic phase. Now what's interesting here is that you can instead of swiping the magnetic field, you can actually keep the magnetic field constant. So you pick some value, like for example where these arrows are, like 0.6 or something like that. You keep the field constant, and then you just change the gate potential, and then you can see if you start, for example, from here, you go from an antiferromagnetic phase, and then as you go up, you make a transition to a ferromagnetic phase. Now, this device can have a potential application in, for example, a spin memory and something like that, but it has a disadvantage because it has it requires an extra magnetic field, right? So what we propose is a new type of device where instead of placing the system in an external magnetic field, we place a bilayer of CRI3 on top of a transition metal dichalcogenide. And the transition metal dichalcogenide, when you shoot a current into it, it has a spin-orbit interaction. So it will create a non-equilibrium spin density, which will then basically leak into the first layer of the bilayer CRI3. So you can basically perform the same switching, like a ferromagnet to antiferromagnet to ferromagnet, without requirement of having any external magnetic field. And also you don't even need like a spin polarized current. So you can just shoot the unpolarized current. The spin orbit interaction will take care for the rest. So to get the non-equilibrium spin density. And so I mean, this is just like a proposal, but we still need to check this. So like we need to perform actual magnetization dynamic simulation. So I'm going to talk about next. So how do we compute the magnetization dynamics? So there are several steps. So we first need to start from the non-equilibrium spin density, which is leaking into this first layer of CRI3. And then we need to compute what is the torque that this spin density exerts on the magnetic moments. So these yellow arrows here. And then based on this torque, we put this torque into the dynamics equation, which is, these are classical, we model this as classical moments. So this is just a classical Landau-Lifshitz-Gilbert equation. So I'm going to explain each of these steps very briefly. So first, the non-equilibrium spin density. So here we have 3 panels for 3 different orientations of the magnetization in the first layer. M along the X, M along the Y, and M along the Z. And then each panel basically shows you the cross section of the spin density when you shoot the current in the TMD in the first layer. How the spin density is spread across the whole system. So here you have for the first layer for the CET and TI, you have a very strong Y component of the non-equilibrium spin density, which is coming from the spin-orbit interaction. Then there is a like 10 or 15 times smaller component which is leaking into the first layer of CRI3, and then for the second layer there's nothing. So basically this tells you that the current is, although like the bilayer of CRI3 is insulating, the current is due to proximity. There is still some current leaking into the first layer. And okay, so regarding details of this simulation, actually this was done by my colleague Kapil Devdoli. So this is a DFT simulation. So we get the Hamiltonian from the ATK from DFT, and then and also these self-energy matrices. We compute what is the retarded Green function for the entire system. For the retarded Green function, we compute the lesser Green function. If you integrate the lesser Green function, you will get the non-equilibrium density matrix. And with the density matrix, then you can measure any operator. We need spin density, so we just basically compute the trace of the density matrix times the spin operator. And this lambda should be, it's some sort of like a, the orbitals are not orthogonal, so there's some sort of like a overlap matrix. Okay, so this is for the non-equilibrium spin density. So the spin density will induce torque. And since we want to model the magnetization dynamics, we want to know what is the torque for any orientation of the magnetization, right? So since DFT is very computationally costly, we cannot, like in real-time simulation, we cannot do the DFT at every time step. So we need to do some sort of like to extract the data from this DFT and then to put it in our like dynamic simulation. So to do this, we basically scan the torque as we change the magnetization on the first layer. So we have 3 axes, 3 planes. Sorry. We scan the torque as we change the magnetization in the XZ plane, XY plane, and YZ plane. And those are these 3 graphs. And then we basically want to interpolate this onto the entire sphere. So basically we have something like a vector field on a sphere, and then we want to know how this vector field looks like, and we're sampling it just over like 3 different planes. And we use this function to fit the torque. It's extracted from this paper. Basically, it depends just on the magnetization orientation, and then there are coefficients that we want to fit, and then there are these 2 vectors. So the z is just like a z-axis, and p depends on it's related to this direction of the like inversion breaking symmetry in the transition metal decalculant. But in our case, this p is more or less it's collinear with it's very close to y-axis. So once we fit the torque, we can actually perform the magnetization dynamics simulation. So we modeled the whole system very simply. So instead of like looking at the actual lattice of magnetic moments, we just we modeled the first layer as a single magnetic moment and a second layer as another magnetic moment. And then the Hamiltonian in this case is very simple. We have just exchange Heisenberg exchange coupling between these 2 moments, M1 and M2. And we have the anisotropy, which is basically responsible for pinning the moments in the plus z and minus z direction. And then when you compute the derivative of this Hamiltonian, you basically get the effective magnetic field, which one atom is like exerting on one moment is exerting on the other. And with this effective magnetic field, we just plug that into the classical Landau-Lifshitz-Gilbert equation for the magnetization dynamics. So this equation has 2 terms. The first term is this green, green arrow, which is basically just a precession. It's responsible only for the precession of the magnetic moment. And the second term is damping term, and is responsible for the alignment of the magnetization with the effective magnetic field. There's slight error. This should be slightly Yeah, it should be slightly tilted. Yeah, and there is also a third term, which is basically this fitted torque. So this is how it enters into the dynamics. So now I'm going to show you the videos for the dynamic simulation. So this is for injecting a simple, just a current pulse. So at these time moments, we just apply some bias voltage, and then you can see that this bias voltage will induce spin orbit torque and then move the first magnetic moment. So you will get transition from the antiferromagnetic phase to a ferromagnetic phase, and then the whole system kind of stabilizes. So you have like a stable ferromagnet, and then when you apply another pulse, it switches back. So yeah, what else? Yeah, so we also did a simulation for a constant for like a DC case when you have a constant bias voltage. In that case, the system goes into this state where basically the magnetizations are kind of like more or less orthogonal to each other. So you have two basically terms acting on the first magnetic moment. You have an isotropy along the z, which is trying to pull it towards the z-axis, and then you have this spin orbit, like non-equilibrium spin densities, mostly, as I said, in the y direction. So the spin orbit torque will try to push it more towards the minus y, and also like this, the pulse case. In the pulse case, when you have the switching, you have like a stable state between the two pulses. Whereas in this case, the state is unstable. So after you turn the DC. The DC voltage, it will simply go back to the antiferromagnet. And the last thing is we sandwiched our system with two graphite electrodes, and we put bilayers of hexagonal boron nitrides on top and bottom, and then we shoot the current in the normal direction, and we computed what would be the tunneling magnetoresistance in this device. Basically, we wanted to know what is the difference between transmissions, or in this case resistance, when you have magnetic moments pointing like up and up down. So this is like a relative change in the resistance here. The theta is the angle between the two magnetic moments. As you already saw, the first magnetic moment is more or less pinned along the plus z axis, so the angle is actually just the angle of the second moment. And we found that the change in the magnetoresistance, it depends whether you have this bilayer of hexagonal boron nitride or not. When there is hexagonal boron nitride, the change is around, like, as you can write from here, it's like 240%, and without hexagonal boron nitride, it's around 40%. So this device can potentially be used as a memory device. And to conclude, so we propose a new way to switch magnetization in bilayer CRI3. We performed a classical dynamic simulation to prove this. There is no, there is no still experiments on this, so this is all still speculation. And the proposed device would have a high tunneling magnetoresistance. Okay, so thank you for your attention.